Okay, so the first part of this lesson, we're going to look at the number 307. It is a topic called change of basis. And usually it is called 基底交换 or something like that. And I'll give you some more example to understand what's going on for this part. Okay. So, say V is a vector space. You just imagine that you are staying in R3. You have a three-dimensional space that you are familiar with. But we have mentioned before that each vector space have some different kind of structure. For example, you can have a basis, probably the standard basis, the x and y and the z, the different directions that we are using before. But it's also possible that you want to use a different coordinate, maybe 45 degree and the other 45 degree, and try to come out with the whole R3 space. So let's say alpha and beta are bases. SES means the plural form. Alpha and beta are both bases of the vector space V. And so what happens is for each of them, you can assume that alpha is composed of some vectors. Call that as V1 to Vn. And for beta, you can call that as U1 to Un. Right, so we know that if we want to write it as a vector representation, say if we have a vector called P, or just call that as V, a vector V, we want to write it as a vector representation with respect to alpha, then we need to find the linear combination of that, say C1 up to Cn. Okay, given a vector V in this space, then you are able to find a linear combination, write it as a linear combination. And in this way, if we have this vector, you can write it as a vector representation, which is recording all the coefficients. And previously, we write this notation as V with respect to alpha. So any vector in this space can be written as a linear combination by recording all the coefficients down here. Then you will get what we call the vector representation. So V can be represented as this way, and somehow you can also write this V in a different way, right? Because V can also be written as a linear combination of beta. Then when you record all the coefficients, it is called the vector representation of this vector with respect to beta. Right, so just give you a quick example that say this is V1 and V2, and you will stretch this one to C1 V1 and stretch this one to C2 V2, so that the vector becomes this vector V can be written as C1 V1 plus C2 V2. But if you want, you can try to find a different coordinate, right? the same vector, you can write it, try to observe the same vector in a different basis. And you use the basis and try to come up with the corresponding scatter. This one is U1, and this one is U2. So you want to consider how much is your U1. So you say D1 U1, and the other direction is D2 U2. So that you know the same vector can be represented by C1 U1, by C1 C2, or it can be represented by D1 D2. So it all depends on your basis, and the basis is like the coordinate system. 就像是两个坐标系 Okay, you have two coordinate system, and the different coordinate system will give you different coordinates. 不同的坐标系会给你不同的坐标。So the main topic, at least for the first few minutes for today, is that what's the relation between these two numbers? How to transform from one side to the other side. Okay, and so a typical example is that you can choose this one as the standard vector, standard basis, and this one is the rotation, right? And so if you use the rotated coordinate system, then you can still write the vector into a vector representation. So here I'll give you a concrete example to see what's going on here. So our V, we'll take it as R2. And for R2, there is a standard basis, E1, E2. And you can consider the other basis called U1, U2. Okay, so I have to tell you what is U1 and U2. Okay, so now let's say we have a vector V. It is known as 3 times E1 plus 4 times E2. Can you try to find what is the V with respect to the vector representation of V with respect to beta? Okay, so it turns out, so let me mention the question again. Here, all of these are my assumption. I set up this framework. Okay, you have two coordinate system. One is the one that we know and very familiar with, and there is a vector called 3e1 plus 4e2. So if you wish, you can draw the vector, draw the picture that you are familiar with. You can draw 1, 2, 3. And try to draw a vector here. This is V. Okay. Now there is a coordinate, second coordinate system that's beta, and beta is using U1 and U2. So if you wish, you can try to draw those two vectors. This one, but it's going to be a messy because unless you really find a grid to draw on it. So basically, U1 and U2 are here. You can do it by yourself, okay? And now U1 and U2 are still like x-axis and y-axis, right? You can draw it by yourself. This is x and this is y, right? So you can still find out, okay, maybe V is here. What is the coordinate of V, for example, right? So basically, you can try to do some calculation. You just try to find out V is equal to 3E1 plus 4E2, so it's 3, 4. And this is actually the same as V with respect to alpha, right? But what you can do is you can try to solve what is D1U1 and D2U2. Try to solve this equation, and then you can get you can write it out. So by solving 3, 4 equal to D1 blah plus D2 something, then you are able to solve D1 and D2. So this part is not too bad, and actually this is the question that you are supposed to know for the quiz just 1 hour later, right? You have to write 3, 4 as a linear combination of these two vectors. So this vector with respect to beta is going to be written as -1 and 5. And again, you can just imagine what's going on the coordinate. This is the U1 coordinate, and this is U2 coordinate. And so you go minus U1 and go up to here. This is the place of V. And my drawing is terrible. I just want to demonstrate what's going on. Okay, so now my point is not asking you to find out such a thing. I'm trying to let you know it's enough to know the following two numbers. Okay, suppose we know E1 with respect to beta and E2 with respect to beta. Then we should know much more about all the information. So before we move on, our goal is trying to understand what is the vector V with respect to beta. But now, instead, because V is composed of E1 and E2, so let's try to understand what's going on for E1 and E2 first. So remember, E1 is 1, 0. 1, 0. So you can look at these two vectors and see, okay, how can I obtain 1, 0? And there is only one way. It is U1 minus U2, which is 1, 0. Okay, so anyway, for E1, you can solve the equation again, and you will realize that E1 can be written as U1 minus U2. And for E2, you can do the same thing, and actually it's not too bad. It's 2 times U2 minus U1. So it is minus U1. Oh, sorry. Okay, now I think I make a mistake. But anyway, that's plus 2U2. Okay, my mistake is like this. It is not supposed to be the representation. It is E1 itself. Sorry if you have written it down. This is my bad. So we try to write E1 and E2 as a linear combination of these two vectors. And then you are able to understand that, okay, E1 and E2, their representation are the coefficients. Okay, so I think I went through a lot of things. Any questions for this part? It looks like quite tiring in the morning, but again, if you have anything that you want to say, you can let me know, so that the class wouldn't be that kind of that quiet or boring. Am I going too fast? Or okay. Anyway, so now here is a different things that you can look at that. Remember, our goal is try to understand what is V, and so now it is enough to write V is equal to 3 times E1 plus 4 times E2, and that is to say you already know what is the representation of E1 and what is the representation of E2. So you are able to say, okay, it is 3 times E1, 4 times E2. So 3 times this part, 4 times this part. 3 copies of U1 minus 4 copies of U1. So it is 3 minus 4, which is minus 1. So you have minus 1 copy of U1. And then you can do the same thing for U2. 3 copies of minus U2 plus 4 copies of 2U2. So it is A minus 3, which is 5U2. And so my point here is try to let you know that for the vector representation of V, as long as you know what are the vector representation for E1 and E2, then you can just use that as a linear combination. Okay, it is equal to 3 times E1 and 4 times E2, so you can write it like this. And by calculating the numbers from the 2 vectors here, 3 copies of this one and 4 copies of this one, then in the end, you will get the same value, which is minus 1 and 5. Okay, and more than that, if in the future, if you have a vector V, which is written as C1 E1 plus C2 E2, then you know that the vector representation of V can be written as this. You put E1 in the front, and the E2 in the second column, and try to make it okay, let me write it again, and multiply by C1 C2 as a vector. In other words, it is these 2 vectors you multiply by C1 and C2. So I'll pause for a while to see if there's questions. I think I'm running through fast in the end, but try to think about that and let me know, is there something that is confusing? For some of the word, my writing is too bad that you cannot recognize what's the word. Okay, again, whenever you have question, just let me know, and otherwise I will keep going. Okay. So asking question is a good way to stop me from going too fast, as always. Okay, so the next example is try to tell you that, okay, something that you have been seen before, but now I'm going to try to mention that again in a different way by the method of changing the basis. Now you see you have a basis, you have two bases, and you want to change the representation. So you write all these things. And the last observation from this example is if you have two bases, then one thing you can do is just try to create something like this. The whole point of this example is try to let you know if you want to transform C1, C2 to D1, D2, then their relation is simply just one matrix. C1, C2 is these two coefficients, and D1, D2 are the coefficients for the other coordinate system. And in order to change 3, 4 to D1, D2, all you need to do is plug in 3, 4 here, and then multiply by a matrix. And this matrix is determined by E1, E2, and their representation in beta. Okay, so later on we are going to see how and what is this matrix. So like I mentioned before, the second example is very common. We have been seeing that several times in your midterm and in other places. So P2 is all the polynomials of degree at most 2. So one of their bases is 1, x, and x squared. And this is called the standard basis. We know this very well. And then somehow you can write it into a different basis, 1, x minus 1, right? This is your midterm, x minus 1 squared. So the question is how to switch or change between the vector representation of alpha and the vector representation with respect to beta. Okay, so I believe you have been doing this several times. For example, this one can be represented as alpha easily, right? So let me write it down. 1 can be represented by alpha as 1, 0, 0. And x minus 1, this vector, can also be represented through alpha, which is minus 1 and 1 and 0. So you can write all of these in terms of 1x and x squared. And basically that's what we call as expanding the polynomial, 对多项式展开. So when we write a polynomial, there are different ways of writing that, and there is a standard way of writing that is through c1 plus c0 plus c1x plus c2x squared, that kind of thing. 所以每个多项式理论上都有一个很直接的写法 and actually that's the vector representation with respect to alpha. Okay. So this one is going to be 1 minus 2 and 1. So now you know, suppose P is a polynomial that is written as d times d11 plus d2x minus 1 plus d3 x minus 1 squared. And you know how to expand that, right? You just expand everything and then you are able to find the vector representation with respect to alpha. But because now we already have all these vectors, so all you need to do is try to write all these things as a matrix and try to write d1, d2, d3 so that d1 will correspond to the first column, d2 will control the second column, while d3 control the third column. And through this way, you know what we get is actually the vector representation of P with respect to alpha. And if I call this matrix as A, and this one is actually the vector representation of vector P with respect to beta, then we come up with a relation saying alpha and beta, their relation is just by multiplying a matrix A, then you are able to switch the two representation. And more than that, you are able to find out, if you wish, you are able to calculate A minus 1. A inverse is this quantity. Through some calculation, you should be able to find it out. Okay, then this tells us that not just you can switch from beta to alpha. If you want to switch from alpha back to beta, then simply just multiply by A inverse. So if you have P alpha and you want to switch that to P beta, then all you need to do just multiply by A inverse. Okay, so we're almost ready to describe the definition of the change of basis matrix. Basically, we are going to tell you what is this matrix and how to obtain this matrix, as you have been seen from these two examples. And again, before I move on, I would like to pause for a while to see if there's any questions. Okay, so now we're ready to talk about the formal definition and just give you a very basic idea first. And for example, how do you come up with this column? This column is actually taken from one, so you have a U1, U2, U3, right? You take each of the vector, U1, U2, U3, and try to write it as the vector representation of the other bases. So U1 with respect to alpha, U1 with respect to alpha, U2 with respect to alpha, U3 with respect to alpha. And then in this way, you are able to switch from beta to alpha. And if you come back to the previous page, in that case, you want to switch from alpha to beta, then you take alpha has E1 and E2. Then you take E1 with respect to beta, which is here, E2 with respect to beta, which is here. So E1 with respect to beta, E2 with respect to beta, then this come up with a matrix that you can see how to find it. So overall, the formula is like this. Okay, so that alpha, beta be basis of a vector space V. And for some reason, we need to know what are the vectors in alpha. Okay, and our goal is try to switch from alpha to beta or the other way around. So what we called the change of basis matrix, the one that we have been seeing several times, it's a long term. In Chinese, 通常我们叫做基底转换矩阵。用来做基底转换用的一个矩阵。Okay, so the change of basis matrix, you have to specify you are changing from alpha to beta, from one basis to the other basis, and it has the form that for each column you take one vector from alpha and write it as a representation with respect to beta. And you do this for each vector in alpha. And such a matrix is denoted by this notation. So the place that alpha is taking the role is providing all these vectors. Okay, alpha is providing the vectors, and then you write it with respect to beta. So beta is used for finding the representation, and alpha is providing the vectors. And before I move on, the symbol is a bit weird, so let me explain what's going on with this notation. Okay, so in the future, all the time, whenever you see these things, you will see alpha or beta. If it is a matrix, then you will see two bases. But if it is a vector, you only see something like this, right? Okay, so if you have two bases, you read it from bottom to top. So it is from alpha to beta. And this notation of bracket is called the matrix representation, which we will talk about next lesson. And this ID is the identity map. Actually, we have been mentioned that before. ID stands for identity map, which means that you are sending vectors from Rn to Rn without changing anything. Okay, my writing is very small, but if you cannot recognize my word, let me know. So overall, this notation is saying that, okay, I have an operation that is basically changing nothing. I'm not going to change anything about the vector, but I'm going to change the perspective, 观点, from perspective of alpha to perspective of beta. 你从 alpha 去观察它，变到从 beta 去观察它。Okay, but you are not changing anything. Next lesson, we're going to say, okay, this part can also be changed by something else. But at this moment, you can just remember this as the notation which record alpha and beta, or there are some deeper meaning about this ID and this bracket. The computer don't want me to continue, right? Okay, unfortunately, we have to continue. So the last part, let me... Seriously? Okay. If you cannot deal with some problem, then kill it. Okay, bear with me. Just the last few minutes, I want to finish this section. Okay, good. Okay, really, the last part I want to say, whenever you see this notation from today and many concepts related to this part, you have to take it as an action, right? For example, this is a rotation, and you want to consider the rotation, and you want to switch from alpha to beta. Okay, you have two things you have to consider, but at this moment, forget about ID. Just remember that you are switching from alpha to beta. So now the following formula will make sense, even though we did not prove that. Okay, so first of the things, what is the change of basis from alpha to alpha, right? You have a vector representation of alpha, you want to change that to vector representation of alpha. 你从一根向量变成同一根向量. Okay, then that's by the identity matrix, I. Okay, and on the other hand, if you have alpha change to beta, and somehow you have another basis, which is gamma. So alpha to beta and beta to gamma. And remember, when you are multiplying something, you multiply the vector on the right. Okay, so a vector with respect to alpha come in becomes a beta. And then this disappeared, then all these becomes a vector representation of beta, and beta becomes gamma. So this one is actually the same as from alpha to gamma. You skip the middle part because they disappeared. And so similarly, if you have something that you want to change from alpha to beta and then change beta to alpha again, and remember it is alpha to beta, it is this direction, alpha to beta, and then beta to alpha. Okay, so it is ID alpha to alpha, which is identity again.